Hello everybody, we're back. We are going to take a break from adding to the derivative pile to do a short section on how we use derivatives. One of the things that's really important going into the AP is not just knowing the mechanics of doing a derivative, but the big idea behind a derivative. What it is, what it gives us, and we've talked already about the idea that the derivative is slope. It's the slope of a function. But one of the things that we need to remember is that a slope is nothing but a rate of change, right? That's all it is. It's the rate at which one variable changes with another. Now, we get really used to the fact that in math, slope is one very specific change, right? It's a rise over a run. It's a change in y over a change in x. But in calculus, we have to remember that if I do the derivative of any function, what I'm getting is an equation for slope, that's true, but I'm also getting an equation for how one quantity is changing with respect to another. So, if we take the derivative of any equation, what we're going to have in our hands, whether the variables are x and y or t or q or whatever they are, is an equation that describes the rate at which one variable is changing compared to the other, specifically the rate at which the dependent variable is changing with respect to the independent variable. And we're going to be able to control that a little bit too in some future sections. But the key right now is to understand that yes, a derivative is slope, but slope it's just a really neat way of saying rate of change. And it doesn't necessarily have to be how x is changing with y or how y is changing with x. It could be how any quantity is changing with any other quantity. So for example, if you have a function that is giving you the position of some object over time as it compares to time. So after 3 seconds it's here, after 5 seconds it's here. It tells you where the object is in space. If we take the derivative of that function, what we get is an equation for the change in position as it relates to time. So a change in position over a change in time. In other words, if I took a graph that was position versus time, and I got the slope of it, the change in y would be position, the change in x would be time. And what I end up with is a change in position over a change in time. We've known since 6th grade science class that that is a speed. That's how fast something is going. Now, if all you have is a finite change in position and a finite change in time, then what you have is an average speed, right? It's those the old train problems that it traveled this far and it's this how long it took it, how fast was it going, but it's an average speed. What we're able to do now that we have a derivative is get an exact instantaneous, right? How fast is it going right now? How fast is it going right now? Again, it's not always just going to be speed. It could be any two variables. So I'm going to start with one that gets me every time. I never stop being amazed by this problem. Okay. It says find the rate of change of the area of a circle with respect to its radius. So I need to know how area is changing with radius. So I need an equation that relates the area of a circle to its radius. Very good. Very good. Area is pi r squared. We didn't even have to look that up. Didn't even have to. Okay, so I said earlier when we were learning the different notations for derivatives that sometimes prime notation was nice and sometimes dy dx notation is nice. I want to point out that this is a time when I think dy dx notation is nice, and here's why. I'm about to take the derivative of this, right? I'm going to take the derivative of a. I'll take the derivative of both sides of this equation. If I write a prime, that's going to tell the world, yes, I took a derivative. But what it doesn't tell us is how area, so we know, I don't want to say this, it tells us area is changing, right? We know that derivative is a rate of change, but it doesn't tell us what the other quantity is, right? Is area changing over time? Is area changing as the color of the circle changes? We don't know, right? We don't know what the other quantity in play is. If we use dy dx notation, though, we would know what the other variable in play is. We would know what the other quantity is. So in my equation, the other quantity is radius. So instead of writing a prime, I'm going to write dA dt. Now, this is a little bit more than notation at this point. Notice this is a teeny tiny change in A over, I really wrote T. I really did. See? It's a good thing it's a little bit more than notation, huh? Boop. Let me just back myself up. The other quantity is radius. So when I take this, instead of writing A prime, where's my pen? I'm going to write DADR. Right? This is now telling me this is a tiny change in A over a tiny change in R. In other words, this is the rate at which area is changing with respect to R. So as R changes, this is what it does to area. Now, if I go to the other side, take the derivative of pi r squared, I get 2 pi r. I'll give you a minute with that. I'm consistently fascinated by that. And look how neat this is. Again, like I said before, this is more than just notation at this point. These are two separate quantities. We call them differentials. A teeny, 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 tiny change in A and a teeny, 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 infinitely small change in radius. These are deltas, right? They're just infinitely small deltas. So just like with deltas, I could break this apart, right? I could say, you know what, I'm going to go ahead and multiply dr to the other side. Okay. Now, why would I want to do that? Okay. It's telling me I have an equation now for how area, the change in area, and I can see what it depends on. It depends on two things. It depends on the radius right now, and it depends on how much you plan to change the radius. So for example, if I start here and I make my dr this piece here, notice the area I've added. This isn't exact, it's going to be an approximation, right? Because if you make a finite change, then you're no longer dealing with differentials. So this is going to be an approximation, but the area I add is going to be 2 pi r. Oh my. It's going to be 2 pi r, and it's the distance around multiplied by its thickness, the thickness of the ring I added. Well, the thickness of the ring I added is dr. Okay. So notice if I add this ring right here, I'm adding less area than if I come out here and add this final ring. So in other words, my dr might be the same. The amount in which I change my radius might be the same, going from first ring to second ring, or 3, 4, fifth ring to sixth ring. But what's different is my starting radius. So if I'm going from fifth ring to sixth ring, I have a larger radius to start with. And look at this. If you add the same thickness to this circle, you're adding a lot more area. You're adding more area because you've got to go around the outside, and it's a bigger around the outside the bigger the circle is. So the change in area isn't going to be constant. It's going to be constantly changing depending on how big the circle is at that moment. So the rate at which area is changing in a circle, if you have a circle that's growing, it's not a linear change. It's not changing at the same rate, I should say. Okay. Fun. So you can do this rate any two variables. Now, I will say, AP comes up with some weird ones, right? There's like bananas coming off a conveyor belt a couple years ago. They always talk about the banana problem at conferences. They're constantly giving us equations and forcing us to understand that this is a rate, the rate at which something is happening, which is a derivative, right? And further down the line, we're going to learn more about what to do when we're given a rate. But this is a huge topic, so we have to keep an eye out and get used to working with variables that aren't x and y, right? It could be any variable. If we're looking for a rate of change, it could be any variable. Okay, one of the big applications of this is motion. Now, if you are taking or have taken physics and you've done the equations of kinematics, you are on one hand at an advantage here because you already know a lot of the theory behind this. On the other hand, you're probably going to be annoyed by this because if you have memorized the 3 equations of kinematics, you're not going to use them here. We're going to use calculus to get what we want. And in physics, you get handed the equations and say memorize and use these, right? But in calculus, we're going to same theory, but different way of getting at it. Okay, so we said earlier that average velocity is a change in distance over a change in time. This is your middle school science class speed or velocity, right? It's an average. So if you look at this little graph here, move myself. Okay. If you look at this little graph here, if I take, I'm going to call this point A and I'm going to call this point C. If I connect this point A to this point C and I find the slope of this line, what that line is giving me is the average speed over that amount of time, right? So this is a position and this is time. So we have from A to C some change in position over some change in time. I divide that out, I get an average velocity. That's what algebra gives you. Algebra gives you an average. If you see the word average, think algebra. Okay. What we want from calculus is something different completely. We want to know not what's happening over some interval, not what the average is over some period of time. That's algebra. We want to know what was the rate of change at this instant. In this case, since it's position in time, it would be giving us the velocity at this instant, at one instant. That's our derivative. It's not going to give us an average slope. It's going to give us a slope of a tangent line. So I could take an average from A to B, but I could also, with calculus now, get a velocity at an instant. Okay? So if we call position S, which we tend to do, even though it's awful, then velocity we can define in calculus as simply the derivative of position with respect to time. In other words, if you have an equation for position in terms of time, all you have to do to get an equation for velocity is take the derivative of it. All right, now the sign on velocity, if our velocity is positive or negative, tells us one thing about our object, and that is the direction of its motion. Now, again, for those of you who are in physics, who are used to taking a velocity and breaking it into its components using trig, put that in your pocket. In calculus, we don't do things off at angles. We do one of two things. We move left and right, or we move up and down. We keep it simple, right? So when we're talking about velocity, we're not going to be talking about like, well, the velocity in the y direction, the velocity in the x direction. No, none of that. Our velocities are going to be a back and forth or an up and down. Okay, so if we say positive velocity, that means one thing. If we say negative velocity, that means another, and there's really no in between. Okay, so positive, if something is moving to the right or if something is moving up. This is just the sign convention, right, that everybody kind of agrees on. Okay? If something is moving down or to the left, we say it's negative. Okay? So we'll do something called, when we do like functional analysis, and they'll say, okay, here's a position function, tell me all about it. You know, where is it, what's going on at time equals 2? So we'll be able to say, okay, well, here's my position function, and at time equals 2, this is where it is. And then we can take the derivative and say, okay, well, here's the velocity, and at 2, the velocity is -5. And if the velocity is -5, that tells us something about the way the object is moving. Right? If it's a back and forth situation, then I know the object must be moving to the left at that instant. If it's an up and down situation, then I know the object must be moving down at that instant. If it comes out positive, then I know that the object is either moving to the right or moving up. Right? So they're going to ask us to describe the motion of an object. at a moment in time. That's what they're wanting us to say. Not just find the velocity to tell how fast it's going, but to be able to say if it's positive, this is the direction it's moving, versus if it's negative, it's moving in the opposite direction. Okay, if they ask you for the speed of an object, the speed is just the how fast it's going part. Okay. So if I do a velocity calculation and I get negative 27, we would report the velocity as negative 27, meaning negative 27 with a direction attached. It's meaning 27 meters per second or whatever it is, but with a direction attached to it. That negative has meaning, and the meaning is the direction. If they don't ask you for velocity, if they ask you for speed, then you throw that negative away, because that negative is only telling us one thing, and that's the direction. If they're asking you for speed, they're not asking about direction. So we see these questions a lot where they ask you for the velocity and also the speed, because they're wanting you to know the difference. Velocity would include the sign, because the sign is the direction. Speed would not include the sign. You would drop it. So if the velocity of an object was 27 meters per second, the speed would also be 27 meters per second. If the velocity of an object is negative 27 meters per second, then the speed would be just 27 meters per second. Woo, I just shook myself up. Excuse me. 27 meters per second. In other words, speed is always going to be positive. Always. Because I'm just not reporting direction. And that's all the negative does, is report a backward or a downward direction. Okay. All right, let's do an example and then I'll shut up, because it's already been 16 minutes and you're probably already really bored with me. Okay, I'm gonna move myself again. Okay, all right, so it says a particle moves along a line so that its position at any given time is given by the function s of t, where s is measured in meters and t is measured in seconds. So I have s of t is equal to t squared minus 4t plus 3. And we're given a graph of that function. So we can see its position at any time right here at t equals 0, right? It's at 3. We can tell that from the equation. And then after a second, it's back at 0 again, right? It must have been moving to the left. And then it continued, at some point its displacement or its position is in the negatives, right? It's been moving to the left. And then we can see by 3 seconds, it's back up to 0 again. So this object starts at 3, moves to the left, its position, it goes to 0, and then its position goes negative, and then it moves to the right again. And it looks like its position keeps growing, so it keeps moving to the right. Okay. So let's use our equation to answer these questions. Okay, it says find the displacement of the particle during the first 2 seconds. Okay, remember displacement? Again, from like 7th grade science, this is the same question. It's just now they shoved it into a calculus problem. The displacement is just the total distance it moved, but with respect to direction. Okay, in other words, it's a, dare I say, it's the distance moved, but it allows for cancellation. So in other words, if you walked 3 feet this way and then you walked 3 feet back, your displacement would be 0, right? Displacement is where it is now versus where it started. It's not the total distance traveled type thing. That's a different question. Okay? So if you're on a walking track and it's a half-mile walking track, if you go all the way around the track, your distance would be a half mile. Your displacement would be 0. They're asking for displacement. All you need to know is 2 things, where it started and where it ended. So it says in the first 2 seconds. So I need s of 0, which is 3, and I need s of 2, which is 4 minus 8 plus 3. So negative 4, 1, right? No, negative 1. Okay, so it started at 3, it ended after 2 seconds at negative 1. So my displacement, there was a change of 4 units, but it's important to note that it was a change backwards. So our displacement here is negative 4 meters. And you might be thinking it's strange to report a negative distance. But it's not a distance. It's how the distance changed. So it started at positive 3, now at negative 1. In other words, it started 3 up, 3 ahead, 3 steps ahead, and by the time we were done, it ended 1 step back. So there's a difference of 4 between where it started and where it ended, and it's important to note that that difference was a this way motion. And displacement includes direction. Okay. Part 2, the average velocity of the particle over the first 4 seconds. When you see the word average, you think algebra every time. Every time. Do not take a derivative if you see the word average. It's an average velocity. So all I need to know over the first 4 seconds is how far did it travel and over how much time, right? I need a change in position over a change in time. My change in time is 4 seconds because it says the first 4 seconds. So all I need to know is how its position changed. Okay. So we know that at we know that S of 0 is 3. We've used that before. So now we need S of 4. So that would be 16. Ooh, minus 16. We get 3 again. Okay, so it started at 3, and it ended at 3. Look at this graph. Here it is at 0 seconds. Here it is at 4 seconds. Ooh, what's the slope of that line? A big fat 0. So its average velocity over the first 4 seconds is 0. So our answer here for average velocity is 0 meters per second. Now, does that mean it never moved? Absolutely not. That's just its average, right? How do you get a 0 average? Well, there's 1 of 2 ways to get a 0 average. You could do nothing and just be averaging a bunch of zeros, right? Every once in a while, people choose that. Okay, but that's mostly not the case, right? Usually the way you get a 0 average is you have some positives and some negatives that come together to cancel each other out. And that's what happens here. As you notice, I have my position changing negatively for a while. In other words, it's moving in the negative direction. And then at 2, it turns around and it starts moving in the positive direction again. So it's just that I had some negative motion cancel my positive motion for a displacement of 0. All right. Instantaneous velocity at 4 is a completely different story. Instantaneous velocity at 4 tells us we need calculus. It's how fast is it going exactly at 4 seconds, not an average, exactly at 4 seconds. And so for that, I need a derivative. So if I'm going to find instantaneous velocity, I need to take a derivative here. So derivative of t squared minus 4t plus 3 is 2t minus 4. So if I wanted the velocity at t equals 4, I need v of 4. So that's 8 minus 4, or 4 meters per second. In other words, translation, if you go up here to this graph, the slope of that line right there is 4. That's how position is changing with time at that exact instant. Okay. Now, this last question, describe the motion of the particle between 0 and 6 seconds. I want to give you a way to help you do that description and make sure you don't leave anything out. Okay, we're going to expand on this little chart as we move through particle motion. Whoa, I have to move. Okay. But this is just the first 2 rows, right? There's going to be a 3rd row up here. It's going to get exciting. All right, so first thing I want you to always do, and you've made, this is about to be a sign chart, like what you made with Mr. Slosky last year. The first thing I always want you to do is find the zeros of each thing. So for position, we know our zeros are 1 and 3, right? I can see that on the graph, but I could also just factor this and know that the zeros are 1 and 3. So I'm going to mark 1 and I'm going to mark 3 on my chart. Okay, now what I want to do is put signs I've now divided it into 3 sections, right? The zeros divided into sections. I want to put signs here because when I'm describing the motion of a particle or any object, the sign changes are going to be really, really important to me. So if I put in a number less than 1, so say, I don't know, 0, I get positive, right? Positive position. In other words, it's to the right. Let's assume we're dealing with right-left motion. It's to the right of its starting point. At 1, it has a position of 0. Between 1 and 3, it's moving in a negative direction. Its position, or I should not necessarily a negative direction, its position is negative. So look at your graph. Between 1 and 3, my position is negative. In other words, I'm to the left of my starting point. After 3, where I hit my starting point again, my function goes positive again. So for the very beginnings of being able to describe the motion of my object, I would say it's from 0 to 1 seconds, it's to the right of its starting point. Between 1 and 3, it's to the left of its starting point. And then from 3 on, it moves to the right of its starting point again. Or its 0 displacement. Okay, so let's take a derivative. I want to do the same thing, but I want to do it for velocity. So we already took a derivative. All right, so my velocity is 2t minus 4. So the 0 of that, the part where my velocity hits 0, would be at time equals 2. So I'm going to go up, 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 and mark 2 on my velocity line. Notice on your graph where the 2 is. Your position function is falling, 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 negative slope. And then you're at 2, that's where it changes its mind, right? All my slopes get positive from there on. So before 2, I have negative slopes. And again, if you're not really sure which signs to put here, just plug a number in. If I plug a 1 into velocity, I get 1, 2 times 1 is 2 minus 4, or negative 2. Any number back here will tell you, if you plug it in, will tell you what sign to go to. On the other side of 2, I can see it in my graph that I'm going to have positive slopes, but I can put any number in. Let's put a 3 in. You get 6 minus 4, or positive 2. So on this side, my velocity is positive. Okay, so now I can add more to my story. I can say that between 0 and 2 seconds, I had an object that was moving to the left. And at 2 seconds, that's when it turned around and started moving to the right. Okay. So what I like to do to really help me describe motion, and again, we're going to add another layer to this tomorrow, is I put these vertical lines in every time there's a change. So that I really have 4 different kind of intervals to talk about. 1, 2, 3, and 4. During the first interval, it's moving to the right, or I'm sorry, it's moving to the left, but it's to the right of its start of the 0 point of position. So it started 3, I don't know which way you're seeing me, left or right. It started 3 steps ahead, but it's also moving to the left. At 1 second, that's where it passes the 0. It's still moving to the left. Notice in the second interval there, the negative on the velocity. It's still moving to the left, but it's now past the 0 point. So in that second interval, I have both negative velocity and negative position. So it's passed into the negative position. It's behind the 0 mark, and it's also still moving to the left. At 2 seconds, my velocity switches. Right? So I'm still over here. Notice my position is still negative in the third segment here. I'm still in negative position, but now my velocity has gone I've turned around. My velocity is positive again. So it's moving to the left. Segment 1, moving to the left, moving to the left. Right where segment 1 becomes segment 2, it crosses the 0 point, continues moving to the left. Now it's in a negative position. At 2 seconds, turns around. So in this interval, can't find my mouse. Okay. In this interval right here, I have a position that is behind the starting point. but my velocity is positive. So it's moving back this way, moving back this way, moving back this way. And right at 3 seconds, right here, notice my velocity stays positive. I'm still moving this way, but my position changes to positive. So that's how I know that at 3, it crossed over. It's still moving to the right, but at 3, it crosses over between a negative position and a positive position. And then after that, it just continues, continues, continues. I know it continues because there are no more zeros. There are no more changes. As long as you can factor and create a sign chart for a function, you won't have to worry that you're missing any changes. And we're going to talk more about that in days to come. I am now at the 30-minute mark. Everyone is tired of hearing me talk. I hope you took good notes, and we will add on to this tomorrow. Have a good day.